Hello, my name is Matthew Sims. I'm a fourth year student at the University of Michigan studying chemical engineering. I've spent this past summer 2013 working through the SURE program at UM's Orthopedic Research Laboratories in the beautiful Biomedical Sciences Research Building. My principal investigator this summer was Dr. Ken Kozloff. Ken, among other areas of expertise, does a lot of studies on osteogenesis imperfecta. Osteogenesis imperfecta is commonly referred to as brittle bone disease and affects approximately 20 to 50,000 people in the United States. As its name implies, OI is mainly characterized by fragile or brittle bones. There are several different types of OI, though, which display other related symptoms, such as muscle weakness, hearing problems, excessive bleeding, or breathing problems, among other issues. Mostly, though, patients show an inclination for broken bones. Now you're asking, why are these OI patients more inclined to broken bones? Well, the simple answer is that their bones do not grow or repair damage as well as they should. Through daily activities and exercise, our bones develop microdamage. As long as the activity isn't excessive, our bones repair these microcracks before they become an issue. A runner who never takes a break may accumulate microdamage in their tibia, which eventually turns into a stress fracture. For OI patients, though, their bones fail to repair this otherwise normal microdamage, resulting in readily breakable bones. Now I'll actually talk about my research, which I've titled Ex-Vivo Detection of Bone Microdamage Using Different Staining Techniques. My first goal was to take excised rodent bones and load or fatigue them in order to induce microdamage or microcracks. I had to develop a reliable way to create this damage ex vivo without breaking the bone. My second goal was to take these bones and stain them so that the microdamage shows up on micro or nano-computed tomography or CT scans. Finally, I was asked to recommend a loading and staining procedure that Dr. Kozloff and his colleagues could use in future studies on rodent bones. One of the first things I did after starting in the lab was excise 30 femurs from 15 rats. Talk about hitting the ground running. Now that I had bones to work with, I used this Bose system to develop a cyclic loading procedure with the help of Joey Porosky, a research associate in Dr. Kozloff's lab. The cyclic loading procedure seen here is fairly simple. This is 3-point bending cycled between 10 and 75 newtons at a frequency of 2 Hz for 1000 cycles or 500 seconds. We also use peak loads of 35, 100, and 150 newtons. You can clearly see the bone bending here as it cycles between the maximum and minimum loads, causing microdamage. After loading the bones and inducing microdamage, I stained the bones using different chemical solutions so that the microcracks showed up when I imaged the bones. For this part of the project, the assist goes to Bess Mercuri. The first stain we used was lead uranyl acetate. We made up a solution with uranyl acetate and lead acetate and soaked the bone in it for 1 week. Then we soaked the bone in a solution of ammonium sulfide, which not only smelled like sweaty gym clothes, but turned the bone black as lead and uranyl sulfides precipitated. The next stain we used was barium sulfate. First, the bone was soaked in a barium chloride solution, followed by a sodium sulfate solution, resulting in a barium sulfate precipitate. After staining the bones, they were ready for imaging on our CT machines. We imaged the bones on both our older micro CT scanner and newer higher resolution nano CT machine. Now I'll show you some nano CT images of bones stained in lead uranyl acetate. Here is a vertical section of a femur. You'll notice some damage here. This is where the machine contacted the bone and a lot of damage occurred. There is also some noticeable micro damage below and above. Finally, the stain highlighted vasculature in the bone really well, as circled here. This was an unintended but intriguing find. Here is a picture taken of a 3D image. The stripe at the top is a clear microcrack. This concludes the summary of my summer research. I hope you learned something and thanks for watching.